Alright, good afternoon everyone. So today we're actually going to start a new unit. We're going to talk about matrices for these next several lessons. And our aim for today is how can we convert systems to matrices and solve. For you do now, it's considered the 3x3 system of linear equations shown below. Start solving the system by adding equations A and B as well as A and C. Okay, I'll give you another 30 seconds. There's a lot of definitions I want to go through today, so yeah, just take another 30 seconds, then we'll get to the rest of the lesson. Okay, so again, if you just came in, today we're starting a new unit called matrices. So, yesterday we talked about polynomials, and we're actually going to come back to polynomials after we finish matrices. The last several lessons of polynomials require us to use matrices. Or rather, I shouldn't say require per se, but it'll be helpful if we had matrices at our disposal. Okay. Anyways, I'm gonna scroll up to the solution for the do now. Again, there's a lot of definitions we need to go through today as our intro lesson to matrices. So here it is. Okay, so again, as the do now prompted us to do, we're going to add equations A and B as well as equations A and C. Okay, so A plus B is going to be equal to 8x minus 2y equals 50. And then for A plus C, that's going to be equal to negative 2x plus 5y equals 1. All right, so that's our first step in solving this system. Next, we're going to multiply this second equation, A plus C, by 4 to get negative 8x plus 20y equals 4. And then now we have two equations with, this one has negative 8x and this one has positive 8x. So if we add them together, we can eliminate the variable x and then solve for y. Okay, so this equation is A plus B. And this equation was 4 times A plus C. Right, that's what we got there. And then we're going to add these two. We're going to get 18y, right? Negative 2y plus 20y is 18y, and then 50 plus 4 is 54. And then from there, we're going to divide both sides by 18. We're going to get y equals 3. Okay, so now that we know y equals 3, we can solve for the other two variables. So from this equation, A plus C, we can plug in y, right? So negative 2x plus 5y equals 1. That was this equation, A plus C. Plug in y equals 3, we get negative 2x plus 15 equals 1. Solving further, we are going to subtract 15 from both sides. We get negative 2x equals negative 14. Then x equals 7. Okay, and then this last equation is what we're going to use. Technically, you can use one of the three, any of them that has z to solve for the last variable. I'm going to use the equation A. So here we have 2x plus y plus z is 15. And we know that x equals 7, right, which we just solved for. X equals 7, y equals 3, and then you have the plus z equals 15. So 14 plus 3 is 17, so 17 plus z is 15. I'll write that here. And then z equals negative 2. Okay. Actually, I won't write that again. That's on the next line. Okay, so z equals negative 2, and then at that point we have all three variables. X equals 7, y equals 3, z is negative 2. All right, give you another sec to copy this, and then from there, we'll move on to our lesson for today. All right, anyone still need to copy the solution? please type in the chat or speak up. Okay, now that I'll move on. All right, so let me give you an overview of the rest of the lesson. Again, today we're talking about matrices for the first time. So there's going to be a lot of definitions that we need to go through. So yeah, we're first going to define what a matrix is, then we're going to follow up with an example, and then we're going to talk about how to solve a matrix. So this thing called, well, we're not going to get into the name of it today, but it's called Gaussian elimination, but yeah, I'll show you the actual procedure later on. And then we'll close with an example. We probably won't have time to get to the worksheet, so yeah, example is what we'll end with. Okay. All right. So, all right, this italicized part you don't have to copy down. There's just the motive behind like why we're learning matrices. So matrices are a way to represent a system of linear equations. They're especially useful when we have large systems like a 3x3 or a 4x4. There's also a whole class that you can take here at Bronx Science that's spent on the theory and mechanics of matrices called linear algebra. Okay. But in the meantime, I want you to copy this, so the definition of a matrix. And can I get a volunteer to read this first part, please, like two-way? All right, we'll go to Paramita.
In summary, a matrix is 1, a rectangular array of numbers, 2, has dimension m times n, where m is the number of rows and n is the number of columns.
All right, thank you for that. So, yeah, so rows are horizontal, columns are vertical. So, like, same thing with like architecture, right? Columns of like a building, that would be vertical. Yeah, these are just two examples. 2x3 matrix, so 2 rows, 3 columns. It would the one shown on the left, and then a 1x3 is 1 row, 3 columns. Okay, does anyone still need to copy this first part? Please type in the chat or speak up. Okay, not then I'll move on. Okay, so next now that we know like the definition of a matrix, so it's a pretty simple concept, right? You're just like an array of numbers. But again, if you take linear algebra, right, in that context, you're going to see that matrices can actually be representative of vectors, right? The same vectors that you see in physics class. And from there, you can like come up with like a lot of different conclusions and theorems about matrices. Anyways, we're also going to talk about solving systems of equations using matrices today. So this is just one example, right? So we can, please copy this down as well. We can use a matrix to write and solve systems of equations. First, we turn the system into a matrix. So this one is really simple as well. You just write the coefficients, right? So here, this first equation, we have 3, -2, 1, and then the other side is -5. So you literally just write those numbers in the first row. The second equation is 1, or x plus 3y minus z equals 12. So the coefficients would be 1, 3, -1, 12, which we have in the second row. And then the last row, we have -x plus 4z is -9. So we have -1 plus, -1, 0, 4, and -9. Note that you do have to have a 0 to represent the 0y. So copy that down, and then we'll get to the next set of notes. Okay, anyone still copying this part 2b, the example? Okay, not that I'll move on. Okay, so after we set up our matrix, right? That's an easy first step. We need to talk about this thing called row echelon form, right? This is going to be our goal in solving a matrix. So you'll see what I mean when we do an example, but yeah, our goal is to get in row echelon form, and we'll talk about how to get there next. Okay, but yeah, first to describe our goal, here it is, row echelon form. Our goal is to get the matrix to be in row echelon form. A matrix is in row echelon form if it satisfies the following conditions. All right, can I get a reader to read 1, 2, and 3? All right, we'll go to Sam.
A matrix is for the first point, the first non-zero number in each row from left to right is 1. Second point is the leading entry in each row is to the right of the leading entry in the row immediately above it. The third point is that all rows consisting entirely of zeros are at the bottom of the matrix.
All right, thank you for that. So yeah, I know that might be confusing, but it's something that you'll see a lot of, so you'll get used to it. And these are two examples. So the first one is an example of a matrix in row echelon form. The second is a non-example, so this one is not in row echelon form. Okay. And the main thing that you need to be mindful of is that the first number in each row is a 1. Okay, so that's a requirement, right? So from the first bullet point. And then the second bullet point is the leading entry in each row is to the right of the leading entry in the row immediately above it. So how that plays out is that it basically looks like a staircase, right? So if you just draw like lines underneath each leading entry, right, you get a staircase pattern. Okay, so that's basically what the second one means. And then the third one is something that doesn't come up too often, but if it does, just have the rows of zeros be at the bottom. Yeah. Okay. The second one, this is not in row echelon form because this is not in a staircase pattern, right? So as you see, right, it like zigzags like that. So that's not in row echelon form, but this first one is because of the staircase pattern that you can see. Okay. All right. So make sure you have that in your notes, and then now that we know what we're trying to get to, right? Next, we'll talk about how to actually get there. All right, is anyone still copying this part right here? No? Okay, I'm gonna move on then to the next part. And this will be the last thing to copy, and then we'll close with an example. Okay, so now that we know that our goal is to get the matrix in row echelon form, right, that staircase pattern with the ones as leading entries, this is how we get there. Okay, so a couple things you need to know for the moves that you can do in, solving a matrix. Okay, so the mechanics of matrices, they're called elementary row operations, right? We work with the rows. Okay, so by using elementary row operations, we can rewrite matrices into equivalent matrices, and by equivalent matrices, that just means that they have the same solution. Okay, the numbers might be different, but like you're gonna end up with the same solution if you stick to these three elementary row operations. Okay, so first thing you can do is add a multiple of one row to another. Second, you can interchange two rows. Third, you can multiply a row by a non-zero constant. And you might be thinking like, these are the same ones as, solving for a system of equations. That's not a coincidence, right? Because, a matrix is just a way to represent a system of equations, if you see it like that. Okay, so it's the same thing, but again, the procedure is what makes it different from systems of equations. So the procedure like always works, right? That's the usefulness behind using matrices, right? And technically you could do the same thing with systems of equations, but this was developed using matrices. Okay. All right, but yeah, with that being said, can someone read this procedure also? All right, we'll go to Max.
Start by obtaining 1 in the top left corner. Then obtain zeros below that 1 by adding appropriate multiples of the first row to the rows below. 2. Next, obtain a leading 1 in the next row and then obtain zeros below that 1. Then make sure every leading number is to the right of the leading number in the row above it by rearranging rows. Then continue until you have a matrix in row echelon form.
All right, thank you for that. So yeah, again, our goal is to get the matrix in row echelon form. And yeah, this is just basically describing, as you can see, right, we have the ones, right, as in our leading entry, and then we're trying to get zeros below that, so we have that staircase pattern. Okay. So this is just a description of the procedure. Hopefully it'll be more clear once we do an example, which we'll get to next. Okay, is anyone still copying this part? Okay, if not, I'll move on then. All right, so we're going to close with this example. So we're going to solve, so it says the following system of equations. Yeah, so yeah, we're just going to do one example and then we'll close. All right, so here is the system. Here we have x minus y plus 5z equals 3. The second equation is x plus 2y minus 6z equals 7. Third equation is 4x minus y plus 8z is 15. Okay, so first step is simple, right? You just write the coefficients in a matrix. So we have 1, -1, 5, 3 for the first equation, then 1, 2, -6, 7 for the second equation, and then 4, -1, 8, 15 for the third equation. All right, so something that's new with matrices is that to denote our elementary row operations, right? So let me scroll up to remind you, right? Here are the 3 elementary row operations, right? So we're referring to rows here, okay? So this is the notation that we're going to use. So here we have row 2 minus row 1, okay? This is what this first operation that we're going to do says. And the convention is that the one that does not change comes second. Okay, so, or the one that changes is first, rather. Okay, the row that changes comes first. So, okay, so we're going to do row 2 minus R1. So row 2 is the one that changes. So row 2 minus row 1, here we have 1, 2, negative 6, 7. We're going to subtract row 1. Okay, so 1 minus 1 is 0, which we have here in the next representation of the matrix. And then 2 minus negative 1 is 3, right? 2 minus negative 1 is 3, which we have here. Then negative 6 minus 5 is negative 11. And then lastly, we have 7 minus 3, which is 4. Okay, so all we did was row 2, this row, and then take away row 1, subtract row 1. So 1 minus 1 is 0, 2 minus negative 1 is 3, negative 6 minus 5 is negative 11, and 7 minus 3 is 4. Okay. All right, we're also going to, do R3, row 3, plus negative 4R1. Okay, so negative 4R1, I find it helpful to write it down here, right, for reference. So negative 4R1 is equal to negative 4, 4, negative 20, negative 12, right? All we did was multiply by negative 4. And this is, the first row operation that we mentioned earlier, right? Multiply one row and then add that to another row. Okay, same thing that you do for, solving a system of equations, except now we're talking about in the context of a matrix. Okay, so R3 plus negative 4R1 is 4 plus negative 4, which is 0, which we have here. Then negative 1 plus 4, which is 3, which we have here. Then 8 plus negative 20 is negative 12. Then 15 plus negative 12 is 3. All right, and then lastly, I'm going to do row 3 minus row 2. Okay, and that's referring to this one. Okay, so row 3 minus row 2. Okay, so 0 minus 0 is 0. Then 3 minus 3 is 0. Negative 12 minus negative 11 is negative 1. And then 3 minus 4 is negative 1. Okay, and now at this point, right, you notice the staircase pattern. Right, you have the staircase pattern. Oops. So technically this is not in row echelon form yet, right? To get into row echelon form, we need the staircase pattern and 1s in each leading entry. Technically we could do that pretty easily, right? Just divide the second row by 3, and then the third row multiply that by negative 1, or divide by negative 1, right? But I'm going to skip that because we can just solve from there. All right, so now we're going to rewrite it in terms of a system of equations. We have x minus y plus 5 is equals 3, 3y minus 11 is equals 4, and negative z equals negative 1, right? That just came from, these numbers right here, which represent coefficients. Okay, now we're going to use substitution to solve for each variable. So we have z equals 1, right, from the last equation. And then from the second equation, we can solve for y, right? So 3y minus 11 times z. In this case, we know that z is 1. So 3y minus 11 equals 4. And then solving, we add 11 to both sides. We get 3y is 15, and then y equals 5. Okay. Lastly, we solve for x. So for that, I'm going to use the first equation, x minus y plus 5z equals 3. So x minus 5 plus 5 times 1 equals 3. So we have x equals 3. Okay, and that'll be your 3 answers. X is 3, y equals 5, z equals 1. All right, let me scroll out so you can see the entire solution. Okay, all right, so hopefully that was, that cleared things up for how this procedure works. We're going to get a lot more practice with it, both on the homework and in class. So don't worry if the notation seems unfamiliar. It should, because it's your first day, right? All right, so while you finish copying that, let me close with announcements. The only thing is that there's SGI today, per usual, it's at 247 after 8th grade. Okay, so 247 SGI, drop by if you have questions. But other than that, if you're done copying this, you're free to go, and I will see you all tomorrow.
Thank you. Bye.
All right, take care. Bye-bye.
Thank you. Bye.
You're welcome.